You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoy the podcast, please listen, subscribe, like, and share it with friends. Thank you. Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcast. I have Sarah Bergbreite. She's a professor of mechanical engineering at Carnegie Mellon. And we're going to be talking about her work and research and other stuff like that. So, Sarah, thank you for coming.
Thanks for having me.
Yeah, tell me about your research, and then maybe we'll go a little bit backwards into your origins.
Sure. So my research is primarily at the intersection of microsystems and robotics, and there's kind of two cool areas to look at there. The first one, we use microsystems to actually build tiny robots, and so that goes to robots the size of an ant that can run or walk or jump and be able to get around. Ultimately, very tiny mobile microrobots. The second thrust is actually using microsystems to make improved sensors and actuators for larger scale robots. And so this comes from the idea of we use a lot of microfabrication that's based on microelectronics and MEMS to create very small sensors and actuators that can ultimately improve the capabilities of these larger robots.
Yeah, I used to work at Intel and Motorola in a fab. So they would do, chemical vapor deposition and etching and things like that to make computer chips on wafers. Is that what you're talking about to make some of these micro machines?
Yeah, very similar ideas. We tend to incorporate a lot of materials that somebody at Intel might not typically use. So things like polymers, particularly soft polymers. So things like silicone rubber, PDMS. And that enables a vast kind of materials toolbox that we can draw from to make these very small mechanisms and actuators and sensors as well.
So what's the point of making small-scale robots? Would it be to put inside the human body, or are there other benefits you get from having really small robots with many of them?
Yeah, that's a great question. So one of my kind of ideal scenarios is just you get large N from this. You get a lot of robots, and you can get a lot of really cool things if you can have a lot of robots work together. And so my kind of futuristic scenario is you have a bucket of these small robots that you can just sprinkle over a disaster site to help find people after a disaster, for example. I'd say primarily right now we use them for scientific discovery, in fact. So the idea of trying to understand how things like a frog hopper insect can jump as high as they can, we actually build physical models of some of the important features of that insect and actually use that. We can change the different variables around much more easily in our robot than you could the actual insect, and try to really understand what are the important parts of that make that insect jump as high as it does, or some insect run as fast as it does, for example. So we'd use a lot of these robots to actually better understand the world around us as it is right now and some of the organisms in that world. And then I think another potential thing that you touched on is the idea of medical devices. And so, a lot of the robots that we're talking about are not going to be, you're not going to necessarily have one injected into you and it's going to travel through your bloodstream. Our robots are typically too big for that. So they're on the size scale of millimeters, so more like an ant. But if you think about what a robot is, a lot of the sensors, actuators, mechanisms, computation, right? If you could stick all of that in a catheter, you could potentially do a lot more in terms of surgical procedures than you can right now, and minimally invasive surgical procedures to be specific. So I think all of these different things are kind of fun ideas, and important ideas for these small scale robots.
Well, it seems like with a really small robot, there's a trade-off where you have to have large numbers of them in order to accomplish a task on the macro scale, and they have to be coordinated and communicate with each other. So it probably changes the dynamics of the robot. The communication is probably a lot more important than maybe just the ability of one of the robots itself.
Yeah, it does. Communication is a tricky thing, though. You don't necessarily need explicit communication. So if you think of how ants are able to create bridges out of themselves, a lot of that is just by sensing what their fellow ants are doing, for example. And so you can have this more implicit communication between the robots to do these more complex tasks. And then in terms of kind of capabilities that you can put on these robots, we also work on slightly larger scale robots, so robots that are grams in size. And in those scales, you can actually put, small cameras and radios, and you could use those for things like inspection tasks. So send them into an area that is not easy to get into otherwise. So say the jet engine, be able to take pictures and make sure things aren't going to fail. So there's a lot of across the range of robots that we work on. Like there's quite a range in terms of capabilities ultimately on the robots as well.
Well, what are some of the most exciting potentials that you've identified? You have a lot of projects, but which one do you maybe secretly hope gets there first because of the application?
Oh, because of the application is a important caveat to that. I have the ones that I want to get there first because they're fun. So I think the thing that I find super exciting right now is I always considered myself very much an engineer. Like I design things, I build things. That's what I do. It's very fun. Um, but I think the collaborations I've had recently with biologists over the last 5 years or so, and these applications for scientific discovery are incredibly fun. Like I love those. I love interacting with these people. I love learning new things about, you know, ants and things that people have been looking at for decades or centuries even. So that's something that I really love, and I love getting the capabilities up online to help those folks. I think the most exciting in terms of application is always going to be the medical side for me. The idea that you can, you know, literally help people in terms of both the kind of devices that we would ultimately be able to build, but also some of the sensors that we're able to design that could help people better interface with larger scale robots for things like rehabilitation and the like.
Well, what are some specific applications that you're working towards?
So one application is more on this kind of interface to this human robot interaction interface. So that is we basically designed. This is with my student Louis Dankovich, who's down at University of Maryland still. And basically, we designed this kind of array of capacitors, capacitive sensors that you imagine like the compression bands that you could put on your arm, like a sleeve, basically. And so these are designed to kind of go over your forearm. And with that, along with some machine learning, you can actually detect a bunch of different hand motions and grasps that somebody could actually be doing. And this could be incredibly important for interfacing with a prosthetic or a rehabilitation robot, or even AR, VR type capabilities in the future as well. So I think that's kind of a current project that has a lot of very near term commercial application.
Yeah, I've heard once you get quote unquote small enough, the normal forces that affect robots change, and other ones become stronger than the. I mean, can you talk about that a little bit? Does that happen at the scales you work at?
Yeah, so especially for the small scale robots, the mobile robots that we work on, I think it's not a question of physics changing, which also people often mistake. So we don't go into quantum physics or anything like that. It's all still very common Newtonian physics, but the physical quantities that you care about change dramatically. So In a large scale robot that's walking or running, for example, mass is a pretty critical part of that. And you don't really care about if the foot is a little bit more sticky to the floor. Like maybe you get slightly better grip, but it's not really imperative. It's not going to dramatically affect the motion of your robot in comparison to what mass will. At the scale that we work at, kind of the say 1 milligram, 10 milligram scale, mass is no longer an important force in comparison to, for example, those forces that might adhere your feet to the ground. In fact, some of the little legged robots that we designed a couple years ago, one of the big problems is that once you put them on a surface, you built them, you put them on a surface, they didn't come off. They couldn't actually move because they were stuck just from the adhesive forces with their feet, and their mass was just not enough. Their inertia was not enough to get them going. And so, these are just things that, if you're designing big robots, you just don't think about. And so it just comes down to, changing the kind of models that you use at these smaller scales. So things that you would just throw away as negligible at the big scale, you do actually now care about at the small scale.
So robots, when they get small enough, they literally don't have enough mass to overcome the sticky forces of their feet on the ground?
You can if your material system is designed that way. So that happened to us, and it turned out we could basically oxidize the surface of the polymer that we were using for the legs and the feet, and add effectively a really tiny thin glass layer on the outside of that and make it a lot less sticky, and then we could move just fine. So it just comes down to what those material systems are, but it's something that obviously insects and our small robots depend on to be able to climb walls and grab your potato chip and that kind of thing. But we big robots, once again, it's just not doesn't show up in the models.
Are there any benefits that you can take advantage of at these really small scales? Anything that come into your favor?
Yeah, I mean, you can take advantage of these forces that can be a pain in the butt as well. So, what I just mentioned, the idea of being able to climb, for example, if I'm really small, I can take advantage of these adhesive forces to be able to climb, for example, much better than I could for a larger robot. It's much harder for a larger robot. They'd have to use entirely different mechanisms to do that, whereas I might be able to get away with the same kind of mechanisms. Um, they're much more robust in general, so scaling is in your favor. If you ever watch bugs fly around, they're often just crashing into surfaces and then they're okay. And that's not something that we as larger organisms can do well, or any robots that are larger can do well. And so if I drop my little robot, it's probably fine. Whereas if I drop my larger robot from the same height, it might be broken into tens of pieces.
Okay, because of the low mass, lower inertia, lower momentum, so there's less damage. They bump into stuff or fall.
Yeah, there's less energy in general. So it's just and you actually get some interesting scaling benefits just in terms of kind of beam bending and stresses and strains as well.
Any efficiency in terms of energy use, or is it the same at that scale?
They typically, so there's a bunch of weird metrics around efficiency. So one that biologists like to use is something called cost of transport, and roboticists have kind of adopted this to some degree, but it's basically the energy that it takes to move a given mass a given distance. Sometimes people add gravity to make it dimensionless, but you can imagine energy divided by mass times distance. That metric tends to look really bad if you're really small, because energy doesn't always scale the same way, for example, and so it can go up dramatically. In terms of efficiency in actuators and kind of the things that would ultimately drive your robot, you also end up looking pretty bad. So electromagnetic motors that people use for larger robots can be pretty efficient, like 90% or so. Whereas the actuators that people typically use to drive small scale robots, like the ones that we work on, more in the order of 10% at best, fractions of a percent at worst. And so we tend to tend to have a little bit of an efficiency problem at these scales, but those 10% actuators are certainly on the order of what muscles can do. Typically, people say on the order of 15% per muscle. And so I think that, I'm not terribly concerned about being able to have useful autonomous operation on these small scale robots. A Snickers bar sugar is about an order of magnitude higher than what we can get for lithium polymer batteries. So if you take that into account and the kind of muscle versus motor efficiency into account, maybe you'd last 10 times or, a tenth the time that an insect would last. But I can tell you that the insects that occasionally run around my house can last quite a long time. And so I think you can still do quite useful things, even autonomously in these small scales.
Why is there such a dramatic drop in efficiency because of the type of locomotion?
So that's a good question. Because mass scales down, you tend to be able to take a little bit less advantage of storing energy in springs, for example, and returning that energy. But if you look at, so a lot of our research, one of the things that we've done is actually specifically looked at legged locomotion at very small scales. And so we've designed these physical models. We get around the actuator problem so that we can just look at locomotion by designing these magnetically actuated legged systems. And so in those cases, you can actually still you still get quite a bit of benefit from having compliant legs and being able to use springs. Those were on the order of grams down to milligrams. It definitely gets to be less of an advantage as you get smaller, though. And so we basically still need to look at new models to really understand that a little bit better. And if you run the kind of basic math, there are different locomotion methods that are better at these small scales or in general. So running is obviously theoretically very efficient if you can actually store all of your energy in a spring and then release that as you're running. Can be theoretically up to 100% efficient. Obviously, it's not in general, but jumping, you tend to get kind of a fixed efficiency out of something like that. Flying typically is not that efficient. Things like crawling, you lose a lot due to that interaction with the ground, but that's something you could take advantage of. Once again, those surface forces at small scales. So it's a fairly complicated problem that nobody's really teased apart yet. But it's a fantastic question.
Well, what does nature do and seem to prefer at the scales that you're looking at? Is that a clue? Has it picked the most efficient locomotion types or no?
Yeah, I mean, nature's always a good source to look at, and obviously things at these scales tend to have legs. Smaller, you tend to move through different kind of mechanisms, but things typically for locomotion will walk or run at these scales. Jumping insects typically use more as an escape mechanism, although some insects will actually use that to get from place to place. And flying is obviously something that some insects are able to use as well, but once again, fairly energetically costly to do that. But we can do things in engineering that biology cannot do because of its starting point, and the materials and kind of muscles and such available to it. So we could come up with potentially more clever ideas in engineering as well.
Are there any new clever locomotion types that either you've discovered or you've seen?
So I guess one thing that we've done that I'd say is not at all bio-inspired, but kind of a fun way to get around when you're small is this is work with a student who's at the Army Research Lab, Wayne Sherman, and basically the idea was using the kind of NanoEnergetics to create thrusts. So we were effectively jumping around with little micro rockets, effectively. So you could etch silicon, like silicon as in Si, the element, the silicon wafer, to be nanoporous. So it has all these very small pores, looks kind of like Swiss cheese. and you coat it with an
Yeah.
oxidizer, and you add a little heat, and you're able to get a lot of energy out of that. So the benefit is that we can store our energy already in this kind of form instead of having to convert battery energy to some kind of mechanical energy. And so we can actually use this chemical energy directly to power a jump, which is cool and works reasonably well.
Oh, why does silicon do that when you make it porous like that?
You're getting out of my my scope of understanding. I mean, a lot of that comes down to the chemistry, but basically, it's the surface energy in the silicon and those silicon oxide bonds that are created.
Okay. Huh.
It's,
Any
the nanopores give you surface area. That's what the nanopores are important for.
right, right. Any types of locomotion or things that you're working on, but it's going to be a few years before you get there, but it'll be a big milestone for you?
Oh, I mean, there's always lots of things that'll be a few years out. On the locomotion side, I think the really exciting bit is adding more autonomy to the locomotion. So most of what people have done at the scale is either tethered because you need that power source or magnetically controlled. And we've done both in the past, and I think that we're basically currently working on some new actuators that I think should be able to get us actual autonomous operation at these kind of scales, so kind of say 10 to 100 milligram type scales. And I'm pretty excited about that.
How small of a camera can you make, or how small of a pincer or an arm, or have you found the limits of some certain things that you'd want to put on these objects but you can't?
I mean, you can always do really small things if you really want to. So, I mean, we have people in this department who go all the way down to kind of DNA origami to creating sensors. So, you can create nanosensors if you really want to. I think the size limits for us is often going to be the energy source. So, the battery or any kind of fuel storage that you might ultimately want to use, and protecting that are going to be packaging that effectively are going to be some of the limits. We can make really tiny mechanisms. We can make really tiny actuators. A lot of it comes down to how you interconnect everything, put all of the pieces together. So we've been working on some new microfabrication techniques involving these kind of microscale 3D printing options that exist now. And a lot of that is to be able to get that functionality exactly where you want it to go, and those interconnections exactly where you want them to go. So this is always, I mean, I can make tiny motors, I can make tiny sensors, I can make tiny microcontrollers, tiny batteries, tiny mechanisms. Putting them together, that's the big challenge. And putting them together often in a very 3D way that allows me to transmit my forces in 3D to the world around me.
Why is that a big challenge? What makes it so difficult?
So one reason that's a big challenge is that in order to make the best microcontroller, the best actuator, or the best mechanisms, they're often done in multiple different processes. And then there's a question of, well, okay, I have a bunch of motors or I have a bunch of mechanisms. How do I put them all together? Like, that's really hard to do at the size scales that we're talking about. It's annoying to do oftentimes with those little Legos and stuff. I have kids, and trying to get all the little pieces together can be challenging. Like when you're talking about things that are orders of magnitude smaller than that, it's much more challenging as well. And so I think that's part of the problem. Part of the problem is just, once I've made these things separately, or I make them typically in these very 2D processes. So I would typically think of microfabrication and MEMS as effectively an extruded 2D process. It's really hard to make 3D things in that process. And so that contributes to some of the challenge. And then just, I had a friend at one point who said robotics is the study of connectors. Like, it's just really hard to get all the wiring to where you want it to go. So you're limited in the kind of actuators that you can use because you can't have like 15 different wires going to a leg that's only a millimeter long. It's just hard. So there's a lot of I think fun challenges. in terms of actually putting all of these pieces together.
I guess the smaller you want to make things, the smaller the machines need to be that manipulate the small things. It needs to be even smaller. The wires that connect them with the things that connect them need to be even smaller, and then they're more subject to different effects than the little machine you're trying to build.
Yeah, Richard Feynman gave a talk at one point titled "There's Plenty of Room at the Bottom." We talked about all of these kind of fun engineering and science challenges at very small scales, but one of the things he talked about in that talk was tiny hands building tiny hands building tiny hands. And so exactly the problem that you mentioned of, I need small robots to build smaller robots. And there is some progress on that front. So there are a lot of folks who are looking at these small scale robots for manufacturing type things, including to make other small robots. So there's a lot of fun stuff to be done in that area.
Okay, well, very good. So what's the best way for people to find out more and get in touch with the lab or you? Or?
Oh, probably the easiest way is to search for my name, CMU. That's name Carnegie Mellon, so Sarah Bergbreite, if you can spell it, bonus, right? SARABERGBREITER. So that's probably the best way.
Okay. Well, very good. Well, Sarah, thanks for coming on and sharing your knowledge. I appreciate it.
Thank you very much.
You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you.